Yeah, thank you, and hello everybody. I must be humble and what we saw today, though, I would say the workshop is the advanced workshop for mere mortals. So it's advancement is advance is relative, very relative. So uh, I prepared some notes like every year, and they are in the Moodle course in the discussion forum. And well, the PDF notes are for today and tomorrow. But let's see how far we can go today, and maybe I will adapt it for tomorrow. Um, yeah. So the plan of this workshop is to show a little bit more advanced features of JSXGraph with a focus on new elements. New means which has been introduced since last conference in October 24. And there's some overlap with what we did in this 24 hours in-person meeting in February. And I presented some of it at a Stack conference in Durham. So sorry if you hear it twice. Where are we version-wise? Right before the conference in 2024, we released 1.10.0, and on Monday we released 1.12.0. So everything between is considered as new today and tomorrow. Yeah, then where to get information. So like every year we have the wiki, and we have the evolving examples database, and we have the API documentation. And in all the three places, you see applications, and always together with the source code. So you can start there and try to adapt it to your needs. So regarding how to start, we showed it a little bit yesterday in the beginners workshop. So of course, there are different requirements depending on the situation, like e-learning platform or simple HTML page or whatever. So, but here's the more or less the minimal starting point, an HTML file, which includes JSXGraph from a CDN, and maybe this is optional. Includes the MathJax library to render math symbols. Okay, and now meanwhile 3D is already quite accepted, and so if you want to have want to display in a 3D view, one starting point would be to add this code to to have an initial 3D view, and with some adaptation of the rear planes, how they are adapted. And yeah, and one change which has happened regarding 3D since 2024 was we now have we have worked hard on the depth ordering, so showing hiding elements which are behind other elements, depending on the point of view. And this is done now layer-wise. And I will show it to you in the API documentation. And we will see an example soon. So you can enable or disable this depth ordering with an attribute of the board, and then you can define layers which are depth ordered. So here in the default setting, there are the two layers, 12 and 13. One layer contains the usual 3D elements, lines, curves, and others, and 13 contains the points. So that means, so let's say let's say polyhedra. For two polyhedra, there's a decision which one is in front of the other one. And if there are points, the points are treated separately from the polyhedra now, because points are in layer 13. That means you can want this, or you can, it may be that you have the points in layer 12. You have to move the points in layer 12. But for this setting, it allows you that regardless what's in front, the points will be accessible by the mouse or the finger. Okay, but we will probably see it in the next examples. Yeah, I will begin today with 3D, with development in 3D. And so 3D is programmed completely from scratch. And we don't use any 3D engine, third-party 3D engine, like WebGL or something else. We really project the 3D elements on in our SVG rendering or in the canvas rendering. That means, okay, it has its limits. It will never be that perfect or that fast than like WebGL or OpenGL or some other 3D engines using graphic cards. Yeah, and probably most of you already have worked with 3D. But since the last year, they have been considerably refactored. Because the main reason was we now have 3D transformations. And for 3D transformations, it's nice to have homogeneous coordinates. So what are homogeneous coordinates? For the non-mathematicians, so each coordinate, the coordinates of a point, is an array of length 4. And well, in JSXGraph, it's a little bit special. Maybe in other systems, it's different. But the usual coordinates x, y, and z, these numbers are on position 1, 2, 3 of the array, and there's an additional coordinate w, which is in position 0. Well, you don't have to know the reasons behind it, the mathematical reasons behind it. You just have to know that usually this coordinate W on position 0, it's either 1, it's normalized to be either 1 or 0. If it's 0, then this point is infinitely far away. If it's 1, then it's a finite point. And yeah, okay. This is new, and you have to probably or maybe adapt to it. But for the input of 3D elements, nothing has changed. So you still can supply 3 numbers to um, uh, yeah, to put a point at a certain position, and this still works. But internally, we will work with an array of length 4. Yeah, then we have a new element, a polyhedron. A polyhedron is an element which is defined by a list of vertices and a list of faces. And in this list of vertices, a vertex is either an array of coordinates or a 3D point 3D. And a face, on the other hand, is defined either as a list, it is defined as a list of vertices, and these lists of vertices can be either given as index or as by key. What does it mean? So we start with a simple cube. So we create polyhedron 3D in this 3D view. And we supply 8 points. And you see here it's completely sufficient to supply the points as, let's say, regular coordinates, or in mathematics, one says affine coordinates by the values x, y, and z. Okay, and then it is followed by the list of vertices. And so the first facet or face consists of the first 4 points. This one, 0, 1, 2, 3. Okay. And you can, yeah. So let's have a look at the example in the JS Fiddle. It looks like this. And so here's the 3D view. For the view, it's usually you should disable the panning and the zooming, because dragging around with the mouse should only rotate the 3D view, but of course that's up to you. Then we have this define this view. It consists of 3 input parameters. It means let's do it like this. I show also the 2D axis. Yeah, it's correct. So the first array tells us where is the lower left, approximately the lower left corner of the 3D view. So it's -5 and -3. And then the second shows us the dimension of how much space it occupies in the 2D view. So these are 8 units in this direction and 8 units in the vertical direction. Okay, of course, it's with a rotation, this changes. Okay, then now I can disable the 2D axis again. So, okay, and we have first what else? So we have the rear planes, which are where we only show the rear Z plane. We can also show the other twos, and then it looks like this. But sometimes it's enough to only show one of these planes. Okay, and then yeah, we have a depth order. Let's show you what happens if it's not enabled. Then yeah, it's quite ugly. The faces, they appear in the order of their generation, of their creation, and of course this is not a really good 3D view. And then we have the projection type. These are central or parallel. Parallel is for students sometimes the better one, because you can, if you position or rotate the object in this direction where you want it, then you see the parallel faces. You get a feeling of it. No, but yeah. And what is a trackball? We also have a virtual trackball implemented. So actually, what I'm doing here with the mouse is I'm only changing 2 directions or 2 dimensions of freedom. So if you look exactly, so I can like this, I can move it like this or like that. But if you look exactly, the vertical axis, it never changes. It stays constant. And when I enable the trackball, then I can also move the vertical axis and everything else. Well, it depends on your need, what you want to have. You can, yeah, you have the freedom to choose what you want. Yeah, now this is the cube, and these are the faces. So we have, of course, 6 faces, and I supplied an array, a fill color array in this example, and during the creation of the faces, the fill colors are taken cyclically from this array. So if we only supply 2 colors, then we will only have blue and red in some rhythm, so to say, depending on the order I specify the phases. And additionally, one can style phases individually. For this, I have to surround this phase or the definition of this phase with another square bracket pair, and additionally give the attributes. And this is so. Show it's a color, a black one, and we can make it less opaque. Easily. So yeah, and the standard opacity is 1, so there's no opacity, and this is true for the other faces. Okay. This is one way to specify a polyhedron. The next one is by vertex keys. I'll show you immediately the example. It looks like this. Same 3D view. What I forgot is I have this box, and this is the third parameter. This means the x dimension runs from -4 to 4, y runs from -4 to 4, and z runs also from -4 to 4. You can use different ones. Like -1 to 3, and then it looks like this. Yeah. Okay. Yeah, we have the same cube, nearly the same cube. We have defined, before that, we have defined 2 points. One is at -3, -3, -3. This is the point A, and it's in layer 12. So if you look carefully, and I will change the opacity a little bit. You see this point A is now behind. You don't see this point A anymore because it's behind another face. And if it's layer 13, then you see I have access to I can see this, still can see this point, because maybe I will really want to make this point, have this point accessible, so people can see there is something which they can drag. It depends on the construction. Okay, so yeah. So so this is the point with the label with the name A, and then we have a second point B. This one is fixed; you cannot drag it, and it has the same x and y coordinate as A, but that component is 3, so it's above B. And wherever I drag this A, I drag this B. This B is dragged accordingly. Okay. Yeah, and for the vertices, I supplied still coordinate arrays, but one point, this point A, for this I specify the name of the point, and for this point, for the fifth point, so to say, for that point, I specified the variable BB. So you can use both, whatever you want. It will be recognized. Yeah, and then compared to the others, in the previous example, we have an array of vertices, and we have the faces are specified by the positions of the vertices in this array. And here we have an object, or in PHP, one would say an associative array. Yeah, our dictionary in Python. And so I give for each vertex, I spend a key, and I can access now the faces by the key names. So these are the first phase is consists of the phases A, B, of the vertices A, B, C, and D. This may be sometimes maybe easier to specify. You don't have to count the vertices anymore. And what you can see here, phase is not necessarily two-dimensional. It can be one-dimensional, like this line, or it can be zero-dimensional, namely it can consist only of this vertex. So this vertex is not longer a real 3D point. It's just well, it's just a phase. And then if these points, if these colors don't like, you don't like these colors, you can additionally set attributes later on with the usual set attribute. Okay, this is this example. And then there's another way to specify vertices. It's like this. Same example mostly, but the vertices are now dynamic. They are the output of a function. And now they are and the function can either be one function returning an array of 3 numbers, or an array containing 3 functions. It doesn't matter. So, and then we can manipulate the vertices of the face of the polyhedron by, so these vertices depend all on a slider, this slider S, and we can manipulate the slider and then change the polyhedron. And of course, one can do it like this too. So here we can put different things. Okay. Yeah, okay, these are polyhedra. And what else can we do with polyhedra? we started recently to allow import or to enable import and export to the file format STL, which is one of very basic 3D file format for polyhedra. For this STL, so if you have a 3D printer at home or at work, then you will know what I talk about. STL file format exists in two flavors, ASCII and binary. At the moment, we just support ASCII. Maybe if there's a reason, if there's much request, we can also support binary. Let's see. Yeah, let's start with an example. So here, this is an example. And actually, we have two polyhedras, namely the red one and the yellow one in the middle. And they do come from this string. So we supply a string. And well, this file format, it starts with solid and a name. And then we have facets. And yeah, facets. And then there's the second one. This is the small one inside. And now we have a new JSXGraph has a new option to functionality to parse STL, ASCII STL, JXG Part3D STL, and then it's just that we have to supply this string, and then we will have an array, and we can so an array which contains the construction data for each polyhedra inside of this string. Yeah, and then we can construct a polyhedra. For the parameters or attributes we talk later. Yeah, and then this works. Actually, here's a small restriction. The facets of a polyhedra in STL consists always of a triangle. So there are three vertices. JSXGraph is not that restrictive, so you can supply as many vertices as you want. But the standard format of STL means a facet is defined by three vertices. Yeah. And so actually this is not a polygon consisting of 5 vertices. It consists of certain triangles, and this can be shown with stroke width equal to 1. Then you see the real facets of the dodecahedron. So, okay. Yeah. Okay. And so this is the reading phase, so parse, and then we create a polyhedron out of the data, and we also can export it. Yeah, we can export this 3D format, and hopefully it's here. No, it's not here. It's the next one. The next one, it's here. This is more or less the same. but an output. And here you can, from every polyhedron, you can export the output in STL format and then put it to your printer. Unfortunately, there are two bugs at the moment, or two not so nice things. So if you define, there's no triangulation at the moment. So if you define your polyhedron not only by triangles, but by polygons with more vertices, like squares or rectangles or whatever, then this will be not a correct STL format. And in 1.12, there's a very stupid bug, namely the solid originally is output as a model. So you have to replace it. But this will be fixed very soon in the next patch version. And here's another example, which has been supplied by Tom Barrett, who is in the audience. So here is a icosahedron with a vertex list and faces, and we create the polyhedron out of it, like this. Okay, and Tom also already generalized this idea. There's a well-known generalization of the icosahedron. It's an iterated icosahedron or subdivided icosahedron. You iterate this process to subdivide the triangles. Then you approximate a square. Fortunately, there's a small bug with it with it, so you have these holes in it. So from these holes, we learned a lot of things how to optimize the shading of the polyhedra. Okay. Yeah. And this one, actually, I wanted to show you something, a different one. Actually, this one is now iteration level 3. It's here. Iteration level 3. There are a lot of phases, if you look at it. If we lower this to 2 or 1, then it makes sense to output it, you can take this output and send it to your 3D printer. And Andreas, who's maintaining all the Zoom session, thank you, Andreas. I told it to him yesterday, and he's immediately sent from our office. He sent the STL file to his 3D printer at home and printed it. And the result of the process looked like this. I'll show you the video. So it's with iteration level 2. Yeah, and this is the iterated icosahedron. And here it is. So it is very nice. So this is one, maybe one chance for you to, or you can, if you see an application, you can allow students to drag polyhedra around and then or manipulate polyhedra and then print the output on a 3D printer. Yeah, okay. Now we had this beautiful shading. Yeah, this is, well, we know, this is this one. So as we already saw that you can color each of the faces in the color what you want, or have a cyclic coloring, fill coloring. But another approach is to have a shader. And yeah, and for this you have to supply this attribute shader. And there are two types, namely angle and distance. And so the shading is done, if you supply angle, it's done according to the angle between the normal of the face and the view of the camera, the view direction of the camera. And yeah, and there it's done in the HSL format. You supply a hue value, a saturation, and a range for the lightness. So it's now it's between 60 and 80. So this is very light and this is very dark, so to say. And then you get these shading effects. Probably we will this camera direction, it will be the default, and soon it might be that we add another feature that we replace it by a fixed direction. So we simulate the sun, lightning by sun, in one of the future elements. Okay. Yeah, I would say I'm not really through with 3D today. We will stop now, I would say, and if you agree, and we will continue tomorrow. So, any questions so far? Or questions, remarks, whatever?
Thank you very much, Alfred.
Okay, no questions.
In the chat from Frauke, Alfred.
It's just a comment. So in the moment you're doing flat shading with the light sitting in the camera.
Yeah. Yeah. So at the moment, it's always the angle between the normal of a face in the camera direction.
Yeah.
But yeah.
Yeah, that's what I understand from the computer graphic point of view. Yeah, so this is just a light in the camera at the moment.
Yeah, and this may be a thing of an option in the future, that users can specify a different lightning direction.
Mhm.
It's not a problem anyhow at all. And of course, you can play around with the lightness range. So here, yeah, you can do what you can adapt it to your needs.